rudder earlier this year. Dr. Ferrucci is here to tell us about Watson's development and its capabilities. Please welcome Dr. Ferrucci.
Clicker. So let's see if this works. Yes, who'd you root for? I just wanted to get a sense of what kind of audience I've got going on here. How many people rooted for Watson? How many people? That's not bad. Not everybody, but clearly a majority. That's good. So what I wanted to talk a little bit about was sort of a combination of giving you some insight into the technology itself underlying Watson, but also, given the audience, I thought it would make sense to share some of my experience about, I consider AI perceptions, how people in my journey through this project have perceived Watson from an AI perspective. And one thing I could tell you is that it's been somewhat bipolar. We had you could almost divide the audience into people who thought, well, what's the big deal? Don't computers know everything already? And it's interesting that perception's out there, and I always thought, gee, that's kind of opaque. I mean, I don't think people kind of really get what's hard and what's difficult for computers, and I wanted to talk about that a little bit today. But then on the other end of the spectrum, people who thought, oh my gosh, Skynet, Watson's going to take over the world and eat all of us, kind of thing. And you had both those kinds of opinions, which demonstrated sort of this opaque sense for what's really going on inside of a computer. And I want to talk a little bit about that answer panel with respect to that. As I started to realize this, and in fact it really hit home when I had a radio show interview after IBM announced that we were going to do this thing, and the radio show host got me on the phone and said, so let me get this straight. So you take all the Jeopardy questions and you take all the answers and you put them in a database, and then when Watson sees the clue come up, it looks up the answer and speaks it, right? Luckily it was a phone call because I was rolling my eyes. I was like, what? I mean, no. Not only didn't we have, the answers, we don't even know what the question's going to be. And the host said, well, then how do you do it? I said, exactly. So, so this kind of gives you a sense that, people, their view, I think, of computers are that, there are these big database tables. And, you give the social security number and you look up the address. And this is kind of this mental model for how things are going on. And this answer panel ended up becoming a very important communication, I think started to change people's perception about what was really going on inside this machine. And I think a perception that actually turns out to be more accurate about what's going on inside the Watson machine. And this shows you its top 3 answers, and I'll talk a minute about how it explored many, many different possible answers, and that it computed a probability, a likelihood that that answer was correct based on analyzing underlying evidence, and that it also computed that white line as a threshold. It was only over that threshold, if its confidence was over that threshold, would Watson even attempt to buzz in, assuming it computed that threshold with enough time to even make that decision. So that, that answer panel captured all of that, and I think when people saw that, it sort of broke this perception, oh, it's just looking this up inside of sort of this curated database, and got them to think, gee, what's really going on inside the machine? Part of the inspiration for doing Watson came from IBM's success with Deep Blue, the computer that played chess. And when we think about chess versus dealing with natural language, these are vastly different problems for a computer. In fact, we think about chess as this finite, mathematically well-defined search space, limited number of moves. All the symbols are grounded in that mathematical model. And of course, the search space is huge, and it was an important breakthrough 10 years ago or so to build a computer able to do that effectively. But when I look at that, I think what's more remarkable is that humans can play chess. And when you it's just so perfect in some sense for a computer. I certainly can't. Human language, though, is a completely different animal, right? And here you've got words that by themselves don't really have any meaning. They're not grounded in any formulaic or mathematical model. They're really just navigating the speakers in the context of their memories and their human cognition. So it's a very different kind of animal, and the meaning of words are so contextual. One story I like to tell is that, a common scene in my household is me yelling down to my two daughters, you guys got to come down here and see this. This is really, really interesting. And I'll be making some mess in the kitchen sink or doing some sort of experiment that I want them to see and learn and understand. And I would use this word interesting a lot. And then one time I said, come down here, you got to see this is really, really interesting. And my 7-year-old stopped at the top of the steps and she said, Daddy, I'm not coming down. Interesting things are boring. And in a nutshell, what she's telling me is that she's assigning meaning based on her experience with that word. She wasn't making a joke. That's what interesting meant to her, right? It gave her a boring feeling, right? And that's really what the word meant. So context, of course, is very, very important in interpreting language. When we think about what's hard and what's easy for computers, we know that looking things up in databases is a fairly easy sort of thing, particularly if I can map the question onto an existing schema. Where was X born? I tell the computer, you look it up in the database, you look up the person's name in the first column, the answer's in the second column. So I look up Albert Einstein, I get Ohm. But instead, if I didn't know how to interpret the question ahead of time, I had no idea what question I was going to get. I had to read a bunch of stuff, and among the things I read one day from among his city views of Ohm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. So it's a lot more difficult now. The computer's got to figure out what are the people, the places, and the relationships, and what's birthplace got to do with being born, and how do I really answer this question. Another good example is X ran this. If I know what it means and I pre-program the computer to say, look this up in a database, assign the symbols that are assigned to X with person column, look up Jack Welch, get GE. On the other hand, if it had to read, if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE, maybe it comes up with that Jack Welch was a painter at GE. So with some degree of confidence, right? So it gets much harder because the computer's challenged to interpret the terms and the phrases in the context of the terms and the phrases that appear in the question. I'm just throwing up there a sense of a different domain. I'm going to talk a little bit more about Jeopardy, but I just want to point forward. Dan Cerruti from IBM is going to talk after me a little bit about business applications of Watson. One of them he'll talk about is healthcare. But, just being able to analyze natural language evidence in healthcare, we see lots of different things here. How do I compare meaning when there are so many different expressions? And again, the meaning of those expressions are so dependent on different dimensions of context, like causation and chronology and terminology. Is difficulty swallowing the same as food gets held up? Is that the same as food getting stuck when swallowing? Is a productive cough after a non-productive cough the same thing as a productive cough? Is a fever the same thing as temperature, the same thing as high temperature? Right, so we have lots of location. When we talk about pain, different ways of expressing location and magnitude of pain. Understanding whether these things are the same thing or they're similar meaning or what degree they're similar actually is a very hard problem and requires the analysis of lots of data and the analysis of words and phrases and how they're used in context. So Jeopardy comes along, and it's this very sort of interesting kind of problem that it doesn't ultimately solve the human language understanding problem, and this is not where we are. There's a lot of work to do. But solving it, being able to compete with champions, helps us drive the technology to deal with broader domains, both in the topic area as well as in the complexity of the language. So we have interior design, cellular biology, classic literature, geopolitics, right? So broad open domain, can't anticipate ahead of time what the questions are going to be, how they're going to be phrased, or what they're going to be about. We also have the very high precision to compete with champions, and I'll show you a chart about how high. But also, probably one of the most important and exciting dimensions of the problem was that you had to compute an accurate confidence, meaning that every time you buzzed in to answer a question, you had to have a sense of what's the likelihood my top answer is right, because I'm taking a risk. If I get it wrong, I lose a dollar value associated with that clue. I give my competitors more time to answer the question and then to get that dollar value for themselves. So there's a risk associated with answering each question. So not only did you have to have the precise answer in the number one position, but you had to have an accurate probability that you were right. That probability had to be backed up with some evidence. And I'll talk about how we did that. And ultimately, had to do this very quickly, high speed. Just understanding the question is a challenge. This actor, Audrey's husband from 1954 to 1968, directed her as Rima the bird girl in Green Mansions. Computer has to parse this, creates a syntactic parse, like you would, when you diagram a sentence in high school. But that just tells you sort of, what the subject, the predicate, the object, the predicate, and so forth. But what does it all mean, right? So now you have to apply some interpretation of semantics. Directed what? Like in directing a film, guiding, teaching, leading. Times, durations. Is Rima a person, a bird, a girl, a character? What's going on here, right? So you have to assign semantics. None of these algorithmic techniques are perfect. The syntactic parsing is not perfect. The semantic alignment is not perfect, nor is it complete. Right? We don't understand all the things that Jeopardy might talk about. So all of these are challenges in just understanding the question. What are the different terms referred to within the question or outside of the question is another challenge in this. When we looked at Jeopardy, we looked at 20,000 randomly sampled questions asked about all kinds of things. This gives you a sense of what we call a long tail, sort of a distribution of the kinds of things that we're referred to. This character or this person or this country or whatever. And so things like product, province, senator, disease, object, heroine, month, vegetable, all basically equivalent and just cutting small pieces of the data out. So the point of this slide is that you couldn't sit there and imagine you were going to build a database and anticipate all possible questions or topics. This wasn't going to be the way to do it. The way to do it was to analyze as-is information, existing encyclopedias, dictionaries, thesauri, scripts, plays, books, reference material, whatever you can get your hands on, analyze that in the context of the question, come up with answers, gather evidence that the answers might be right, score it, and compute that probability. About 13% of the questions didn't refer to any class at all, just like this or it. So you had to really use the context to figure out what was going on there. Lincoln blogs, let's see. Treasury Secretary Chase just submitted this to me for the third time. Guess what, pal? This time I'm accepting it. Anybody? Resignation. Did you actually know the historical fact, or did you use a plausible inference? Plausible inference. Right, because you look at the context and you say, what kinds of things could be submitted? And what kinds of things are submitted by an official in the context of a president? It wasn't even worth mentioning. So you came up with his resignation, that's right. But giving this talk to a sixth grade, they used the same sort of plausible inference mechanism, and they came up with a very different answer. But the good news is neither you nor the sixth graders knew the actual history. So one of the things we have to do is learn how words are used in various contexts. And one of the things Watson does among many algorithms is analyzes large bodies of text, produces syntactic frames, as I showed you before, parses it, what's the subject, the verb, the object, then it assigns semantics, and then computes statistics. So it can learn things like inventors patent inventions, officials submit resignations, people earn degrees at school, fluid is a liquid is a fluid. Which one's actually true? If you look at a physics taxonomy, right, fluid is the more general thing. A liquid is a type of fluid. But humans, in regular language, use them somewhat interchangeably, which is important. Because if you're solving physics tests, you want to train on data that allows you to exploit the actual taxonomy. If you're answering Jeopardy questions, fluid, liquid, not a big difference. Right, so it depends on the context and the training data that tells you how to use those words in what context. Vessels sink, but people sink 8 balls in the context of pool. So not only extracting that information and computing the syntax, the semantics, and the aggregate statistics, but then that has to be chopped up with regard to a representation of context. Because you're going to get a different answer if you're asking what kinds of things, if I want to make a plausible inference about what kinds of things may sink, in general, or sink in the game of pool, right? So you need a representation of context. How good are humans at this game? And this is the metric we used to understand what we were really up against. What you see here is a graph that shows the percent of questions answered along the x-axis. You see precision along the y-axis. And what those cloud of dots represent are actual historical Jeopardy games. And what I'm plotting is the performance of the winner of those games. So if you look in the middle of the green cloud, you see the average winner was acquiring about 47 to 50% of the questions, meaning they were confident and fast enough, more confident and faster than their competitors. competitors, so they were able to acquire much more of their share of the game board, and then they did between 85 and 95% precision. The red cloud is Ken Jennings. He, on average, acquired about 62% of a game, extremely confident, extremely fast, and good with the buzzer. He's going to talk later, so he can give you a real explanation for how the heck he did that. But it's really phenomenal performance. The bottom line there is a state-of-the-art question answering system that we've been working on for some time and in good company, and we applied it to the Jeopardy problem and got this confidence curve. The way to read that is, on 5% of the data, it did about 47% precision. As it had to answer more and more of the questions, its confidence went down, right? It's picking those questions it's less confident in, and ultimately plateauing at about 15%. This left an enormous gap between the performance of that system and where we had to go to compete against grand champions. And this is what we faced, and this is the challenge that I signed up for in 2007. So it was get there and compete with grand champions or lose my job. So the underlying technical philosophy, we had to put some stakes in the ground. We signed up to do this in basically 3 to 5 years. We did it in 4, so we landed right in there. But we had to make some commitments. We had to put some stakes in the ground about how we were going to do this. And a few things. One was specific, large, handcrafted models won't cut it. Again, we weren't going to sit there and curate and build a big database we thought was going to address all Jeopardy questions. Too slow, too narrow, too brittle, too biased. We needed to acquire and analyze as is knowledge sources. Second, intelligence from the capability of many. So in other words, a diversity among methods. There was no expectation there was going to be one algorithm that knew how to do question answering. So while you see a Jeopardy contestant, Watson is a Jeopardy contestant on stage, when you pull the covers back, you don't see a Jeopardy contestant in there. You see lots of different algorithms, and none of which, if you looked at individually, would you think, what's that got to do with playing Jeopardy? You'd barely see the connection. So it was this holistic behavior, and of course the interface, that pressed a button and spoke the answers, that gave the impression of a Jeopardy contestant. But really what's underneath there are hundreds of different algorithms that are looking at the data and playing different roles in an overall architecture. So many diverse methods, no single one is perfect or complete. None of them are perfect at what they do. None of them. So this is a big probabilistic machine with respect to the idea that every algorithm is coming up with a confidence in its result, not an exact answer. And ultimately, we had to be able to balance the contributions of all these different algorithms in some sort of meaningful way. And to do that balancing, we had to learn it. It was too complicated for a human to sit there and say, well, I trust this algorithm under these conditions, but not that one under those conditions, and compute all the weights on these hundreds of diverse algorithms. But we used statistical machine learning to do that. And ultimately, there was this belief that we had to pursue many hypotheses. Since we had to defer commitments until we gathered as much evidence and ran as many algorithms as we could, we had to be able to pursue many different hypotheses in parallel. To do that efficiently, we were going to have to exploit massive parallelism. Now, I'm going to preempt a question. A lot of people ask me, well, did you think ahead of time how humans do this? No, we did not take an approach of we're going to try to model the way the human mind works. In retrospect, you may look at some of this stuff and you may see parallels to the way you think the human mind works in terms of many, many diverse independent modules that come together, a massive parallelism. That's true, but we didn't. That's something that you could look at in retrospect and say, yeah, those things are similar. But we didn't start out by saying we're going to model, human cognition. We ended up with this architecture, the Deep QA architecture, that starts with a question and a topic. And then generates many different interpretations, does many searches, generates many possible answers. Let's say, for the sake of discussion, 100 possible answers. Hypotheses, candidate answers. Each of those spawns another thread, and for each one of those, we collect lots of evidence. Say 100 pieces of evidence. So now we have 10,000 evidence answers pairs. What's evidence? A passage, a document, a fact, something that pulled out of an external resource that we thought might be relevant. For each evidence answer pair, we have 100 different algorithms analyzing that evidence, looking for various kinds of features. These algorithms were developed by a diverse set of researchers who said, gee, I have an idea about how to judge evidence, to judge whether or not an answer given that evidence might actually support or refute, whether the evidence supports or refutes an answer for that question, and they'd implement that and we'd learn how to combine it. So now we have this massive parallel machine looking at each of these hypotheses as competing independent hypotheses, gathering and scoring evidence. The one with the highest confidence at the end was the one Watson would look at and say, if the confidence is high enough, it wanted to buzz in and take a chance on answering that question. If it was past that threshold I talked about in the beginning. I'm going to skip this slide because there's not enough time. So using that architecture and populating that with many, many different algorithms and refining those algorithms over time, over that 4-year period, with a very different incentive model within research. We had to really break the cultural norms about how we work together as a team. We put a diverse group of researchers all in one room, computational linguists, machine learning folks, knowledge representation and reasoning people, NLP people, information retrieval people. We put them all together in one room, and we continued to advance the components that plugged into that architecture. And we continue to test, do error analysis, and refine those algorithms. And over that 4-year period, we ended up driving that performance up until this shows the last test done in November 2010. We actually got a little bit better than that. And that confidence curve says that if it had to answer between 60 and 70% of the questions that it was most confident for, it was doing somewhere near 90% precision. This was good enough to compete against champions. Now you had to bring in speed. And you had to bring in strategy and gaming and things like that. But this performance was good enough to compete. Would it mean that you would beat anyone who was up there and played? No, it would depend on the competition. But it means you had a shot. You had a shot at beating champions. It wasn't a sure thing, but you had a chance. And that's roughly where the performance was when we went in to play Jeopardy. Now, from a speed perspective, we took that entire system, ran it on a single 2.6 gigahertz CPU with around 64 gig of memory, and it took 2 hours to answer one question. The Jeopardy producers insisted that would be too boring of a game. So we had to scale that technology out, and because it was a massively parallel design, the scaling, I don't want to claim it was easy, but it was a natural fit. And we were able to scale that computation out over 2,880 cores, and 15 terabytes of RAM. And that's a system that completely self-contained, the system that went up against Ken and Brad. Now, it's interesting from an AI perspective and a point-in-time perspective to compare the performance of what it took to compete at Jeopardy. Right? So here you've got a human with a brain that fits in a shoebox, powered by a tuna fish sandwich and a glass of water. And over here you had 2,880 cores, 15 terabytes of RAM, didn't even go to disk because disk was too slow, about 80 kilowatts of electricity and 20 tons of air conditioning. So interesting comparison about what it took from a machine perspective. And again, point-in-time comparison, but nonetheless an interesting one. The really important point I want to make here is that, and I think this will tie in to Dan Cerruti's talk, who's going to follow me, who's the lead on the business side of this, is when you saw Watson play Jeopardy, it was about question in, answer out. But when you think about that computational paradigm I just showed you, it's ultimately not about giving an answer in the top position, an answer to a question in the very top position. It's really about producing alternatives and the evidence behind those alternatives and accurately ranking and producing meaningful confidences around that evidence. So here's, just to give you a sense, this is a tool we built where we have this question, for example, Chile shares its longest land border with this country. There are actually hundreds of features produced by hundreds of algorithms. What is going on? This is a very complex system. We had to build tools to understand what was happening, to look at how features were preferring one answer over another answer, zoom in on the features that were preferring the wrong answer, the ones that were preferring the right answer, understand what was going on. We'd eventually produce what we called an evidence profile. So this is what really is going to underlie the interaction with Watson in real applications, the notion of an evidence profile and the ability of the user to look at what the computer has come up with in terms of what the top answers are and look at their evidence and the dimensions of their evidence, and then to drill into those dimensions and get to the actual sources that support or refute an answer. So we see negative and positive evidence here along different dimensions. Behind these dimensions are hundreds of different features producing these weights. So you'll find Bethel College and Seminary in this holy Minnesota city. There's a Bethel College and Seminary in both St. Paul, Minnesota, and South Bend, Indiana. unfortunately for the computer. So it has lots of evidence. Actually, the majority of evidence here is in support of South Bend, Indiana, except for the location evidence, which correctly supports St. Paul, Minnesota. But the weight's not high enough. That bar is not high enough. Even though, say, South Bend, Indiana has negative evidence because it's in Indiana, the computer doesn't realize, in this case, that it needs to weigh that location evidence much higher than all the other evidence. We learned from the evidence profile both how to advance the algorithms and make this smarter, but we also learn what the computer's really doing. Why is it making the decisions that it's making? This is what's important in helping humans make decisions in high-value questions like, if you're a patient, what's my likely disease? What's a good treatment option for me? Right? How do we gather the evidence, rank it, and score it? Of course, there's another way humans answer this. They look at holy and they think, wait a second, there's a pun. Holy and St. Paul. St. Paul's clearly holier than South Bend, Indiana. And what's interesting about the technology is that an independent researcher built a pun detector, something that looked for puns in language, with a few heuristics, integrated that into that big system, trained it, and the pun detector actually gained weight and preferred St. Paul over South Bend. Of course, it put Holy Cross, Minnesota in second place because, after all, Holy Cross is holier than South Bend, Indiana, at least from a pun perspective. So when we look at these evidence profiles, we now could start to think about different dimensions of evidence. If we apply this in healthcare, symptoms, family history, personal history, medications, findings become dimensions of evidence. Algorithmic features look for how patient information is expressed and how information is expressed in large bodies of medical content, and start to do a similar thing. Produce many different hypotheses, collect evidence for those hypotheses, and score them using these rich algorithms that look at various kinds of features. So now you can imagine a scenario where all these different kinds of data from many, many different sources are coming together, and the system is evolving. Could be differential diagnosis, could be a set of treatments, and it's evolving evidence profiles and ultimately comparative evidence profiles for presentation to the caregiving team, whether it includes the doctors, the nurses, and possibly even the patients. So imagine a continuously running system that's gathering input data and doing this analysis over large volumes of content to produce these evidence profiles to help people make better decisions and to eliminate some of the natural biases that when a human brings their personal expertise to a problem, they're going to naturally bring biases. The computer can look at many, many more hypotheses and much more evidence to help overcome those biases and make the humans ultimately better decision makers. So that's where I wanted to end my talk. Thank you.
We've got just 2 minutes for questions, but after the next talk, actually, we're going to potentially, if there's time, bring both out and maybe do a little joint Q&A. So just 2 minutes right now, and then maybe a few more opportunities later. Starting here on the left.
Yeah, hi. My name is David Orban. Today we evolve and compete not only on technical achievements, but also on models and how we achieve doing things. IBM is a commercial entity. Watson is a beautiful technology. How many patents protected, and how do you see it fertilizing and helping the open research community achieving even more together with it?
So that's a great question, and we are actually thinking about that a lot. I mean, and obviously, ultimately, you're absolutely right. It's a business question for IBM. But IBM is also interested in engaging and collaborating with the broader scientific community. In fact, the underlying technical architecture that DeepQA was built on top of, technical infrastructure, is UEMA, which was also, I was the chief architect for that. We built that in my team. That's now an Apache project. So that it made sense from a business perspective for IBM to contribute that to open source, and we did. And so I think, we have to keep thinking about it, but we're already talking to some universities about different ideas around being able to provide this architecture as a means for different researchers creating individual components, combining them, and looking at the effects of end-to-end results. And this is a very, very important idea. And I mentioned earlier in my talk how we sort of changed the culture within research. And a lot of academics have been very excited about this. We cannot let individual PhDs pursue their idea in isolation. We really had to look at what the end-to-end system performance needed to be, under the assumption that if we got a system to play Jeopardy, that all the underlying component technologies would advance in kind. And if they didn't, we would learn how to prioritize the research, what really mattered. Because sometimes one algorithm, possibly a much harder one, would actually be, I should say, possibly a much easier one to implement, would eat the lunch of a more complicated algorithm. But if those two researchers and those two approaches weren't allowed to combine to the same system, you wouldn't learn that. So, you keep pursuing the really more complicated one, not willing to admit that, gee, this really easy one actually completely overwhelmed that. By building integrated systems, we learn how these various algorithms interact and overlap. And it's a great idea to support a broader research consortium so that everyone doesn't have to rebuild that architecture and that infrastructure.
That's all the time we've got for questions right now. But thank you so much, Dr. Ferrucci, and we will bring you back if we've got a few minutes in just a little bit.